Hi everyone. This is a one-dimensional steady-state conduction problem involving compost. In the problem, we're given the height of the compost. We're going to measure that in the x direction. The length is in the y direction. So just be aware of that coordinate change. The control volume is shown in red here. The compost is indicated in green. We're given the following information: the ambient temperature, which is shown as T infinity, the heat transfer coefficient, the base temperature, the heat generation due to the decay of the organic matter inside the compost, and also the thermal conductivity. Numeric values are shown here. And what we're going to do is look for these following four items: governing equations and the boundary conditions. We're going to discover a temperature as a function of x, and we're going to look for the maximum temperature and the temperature at the top of the compost. So the bottom of the compost, it's in contact with the ground. At the top of the compost, you have an airstream that provides a heat transfer coefficient of 50 watts per meter squared K, and the outside temperature is a bit warm. It's 40 degrees Celsius. Working down through it, let's be clear on the assumptions. We're assuming uniform K and Q. Q, notice, is watts per meter cubed. It's a steady state problem, and there's no flow inside the compost. We also have to recognize that the compost, or at least assume that the compost is 2 meters tall. That's the distance L. I should write that. This is 2 meters. And it's quite long in length. So we assume, in order to make it 1D, that the y direction, the direction along the ground, is much, much longer than the direction heading from the ground to the sky. So when we go into the partial differential equation, called the thermal conservation of energy equation, we look at partials with respect to t, partials with respect to x on the left side, indicating steady state and convection. Because there's no flow in a steady state, both of those terms go away. The remaining terms, conduction in the one direction, is shown here, and I could highlight that, and the heat generation. So this becomes a ordinary differential equation that is non-homogeneous, and we can solve that equation, this differential equation, for the function of t as a function of x and also the other given parameters if we pull this down, simplify, and go after this equation through integration. If we integrate twice, we'll get there. So we pull out the one. Notice that we went from partial notation to ordinary differential notation, and we've moved one of the dx's over here. When we integrate here, we get rid of this d and add an x and a constant. These are indefinite integrals that we need to eventually evaluate with the boundary conditions. If we repeat that process one more time, we have the dx once again moved to the right, integrate the second time, and you've got t as a function of x. This equation that I'll highlight is the most important equation that we need to work with in this problem. And it remains to be calculated, C1 and C2. So let's apply the two boundary conditions. What are they? Think about that for a moment. The first boundary condition should be the temperature at the base, which was given. And if you assign Tx equal to 0, you can see that T base equals C2. T the base, make sure it's shown here, is 20 degrees Celsius. Now we're after the second C term. How do we do that C term? We notice that at the upper boundary of our control volume, we have an energy balance. So let's just make sure that we get that. So this is an energy balance at control volume surface, basically saying Q from conduction equals Q to convection. We've also neglected or assumed that radiation is not important. So if we have this relationship, let's now do the math. We evaluate on the left-hand side a derivative of this equation shown in the red box with respect to x. You can see that the qx squared would go to 2qx. The 2's would cancel, and you'd end up with this after substituting in for L. So you have equation 1 saying this. The problem with equation Roman numeral 1 is that we have two unknowns, C1 and TL, the temperature at the surface, that we don't know. However, fortunately, if we remember, having solved for the original C2 term, this equation now becomes another equation that has T and C1 in it. So, fortunately, combining Roman numeral 1 and Roman numeral 2, we have two equations, two unknowns, C1 and C2, C1 and T, T at L, and what we're going to do is solve these two equations by direct substitution. We directly substitute in the values. Notice how this side is reduced to that, and if TL is placed in to this equation, you get the right-hand side. Now it's a matter of algebra. Walk through it, pause the video if you need to, but we can solve for C1. C1 is 80.06 K per meter. Notice I've also noted that a delta K and a delta C are equivalent. Now that we have C1 and C2, C2, remember, is the T at the base, also called T1. We can solve for an equation now of T of X. If we want to, so what we've done so far, just to recap, is we've applied or found or reduced the governing equation. We've discovered a temperature as a function of X. Now we're going to look for the maximum temperature and the top temperature. So how would we calculate the max temperature? Well, fortunately, we'll also go back. We've done some integration. Now we're going to do an evaluation for a maximum. And if we recall once again from calculus that the derivative with respect to x, a 0 of that first derivative represents a max or a min, so we solve for it here. It's a value of x equal 1.14. Since the second derivative is always negative, 1.14 must be a maximum. When we put in that 1.14 into the boxed equation for T of x, we come up with a maximum temperature of 65.8 degrees Celsius. At the top, we've been given 2 meters. We find that it's 40.1 degrees Celsius. So when you review this problem, it's relatively straightforward. I think the big challenge was identifying the control volumes, identifying all the key parameters, reducing the partial differential equation, applying the boundary conditions. The first one's trivial. The second one takes more algebra and also some recognition that you do have some information from a previous equation now that you have solved for C2. Once the algebra is done, it's a matter of plugging in values that have been derived from calculus again. And I hope this has been helpful. Please reach out if there are further questions, but I hope this brings clarity to this problem. I think we can also explore it in Excel. Feel free to do so and reach out if anything is unclear. Thank you.